So I'm happy to introduce Shane Chern from Penn State, who's going to talk about the EGZ theorem and a formula of Vlad-Deda-Jovovic.
So first, I want to thank the organizers for arranging this fantastic meeting and also gathering us together. So today I want to talk about the EGZ theorem and also a formula of Jovovic. So from the title, you can see that the starting point is the EGZ theorem, which was discovered by Elders, Ginsburg, and Ziv in around 1960s. And this theorem says that, suppose we have a set of integers of size 2 and minus 1, and then we want to choose some subsets from this original set. And then we can always find some subset of n elements, so that if we sum up all elements in this subset, then this sum is a multiple of n. And also this result has some nice generalizations. So for example, given an abelian group, then we can define the EGZ constant. And also we have some higher dimensional extensions. For example, the second dimensional extension is called the Chemnitz conjecture, which was proved, say, in 2003 by Christian Reher and independently by Carlos Di Fiore. So here a question is that we can see this EGZ theorem is an existence theorem. So a question is, say, suppose we have some nice original set, say the set of the first 2 and minus 1 positive integers, then can we count the number of subsets we desire? And this formula was later conjectured by Jovovic and then proved by Alexeyev. So this theorem says that suppose we have the first 2 and minus 1 positive integers as the original set, and then we want to choose some n-member subsets from this original set, and so that the sum of the elements in this subset is a multiple of n. Then the number of such subsets can be counted by this formula. So here, this phi function is Euler's torsion function, and here we also have this central binomial coefficient. And this sum is over all divisors of n. And here I will give a sketch of Alexeyev's proof. So here we can see that S of n is actually the coefficient of x to the power of ln times y to the power of n in this finite product. This is because here the exponent of y counts the number of elements in the subset, and also the exponent of x counts the sum of all elements in our desired subset, and then we sum them up so that we have this expression of S of n. And here we notice that the exponent of y ranges from 0 to 2n minus 1. So the only multiples of n are 0 and n. And also here the exponent of x is a multiple of n. So this means that we can use the orthogonality of roots of unity to dissect this sum. This means that, say, suppose we have a Fourier series in this form, and then we want to dissect, or we want to take out all arguments n that is congruent to small h mod some capital H, then this slice of the generating function can be actually computed in this way. And here, since the exponent of y is a multiple of n, the exponent of x is a multiple of n. So this means that we can use the dissection formula twice to give a new expression of S of n. So this means that S of n can be actually written in this way. So here, this -1 comes from the exponent of y to the power of 0, because we need to discard that term since the exponent of y is just n. And here, the second term comes from the dissecting formula. So here we have a double summation, and here this product is the generating function, or the product here. And then we can just set D to be the GCD of n and j, and then we write n prime as n over d, so that we can further simplify this expression in this way, and then we can use some computation involving the metric functions to further simplify this expression, and then the communication is quite complicated, so I will not give the details here. And from Xjiv's proof, then a question is, do we have any simple proofs of this formula of Jovic? And also another question is, do we have any extensions of Jovic's formula? So let's go back to this result. So here we have three directions to generalize this result. The first thing is the original set. So here, the original set is a set of first two and minus one positive integers. So the size is 2 and minus 1. Then can we extend the size to be, say, one less than a multiple of 1, say some un minus 1. And the second thing is the size of the subset. So here we require that the size of the subset is n. Then can we just extend the size of the subset to be some v times n? And the last thing is we require that the sum is a multiple of 1. So it is congruent to 0 mod n. Then can this sum be congruent to, say, some c mod n, where the c is given? So here we have three directions to generalize this result. And actually, we can combine the three directions together so that we have this theorem. So here, suppose we have two positive integers u and v, and also we have another integer, let's say c. Then suppose this counting function s of u, v, c, and n counts the number of subsets of this set 1 up to un minus 1, and also the size of the subsets is v times n. And also we require that the sum is congruent to c mod n. Then this counting function can be actually computed nicely by the two cases. So here in the first case, n is odd, or n and v are both even. And also in the second case, the n is even and v is odd. So here we have two functions in the summand. The first one is this mu function, which is the Mobius function. And also we have this Euler's totient function. And the only difference between the two cases is that in the summand of the second case, we have one more factor, which is -1 to the power of d. And here d is the positive divisors of it. And so here I will give some examples regarding this theorem. And due to the time limit, I will only talk about the first example. So here, let's just choose some values of n, u, and v. And then, so for example, we choose n to be 3, u to be 2, and then v to be 1. Then the size of the original set is un minus 1. So 2 times 3 minus 1, then we have 5. So here the original set is 1 up to 5. And then what's the size of the subsets? It is v times n. So here we need to find all three member subsets of this original set. So here we have 1, 2, 3, 1, 2, 4, etc. And then we sum up all elements in these subsets. So for example, in the first one, we have 1 plus 2 plus 3, which is 6. Then mod 3, we have 0. And then 1 plus 2 plus 4, 7, mod 3, 1, etc. And then we count the number of subsets such that the sum is congruent to 0 mod 3, then we have 4. 1 mod 3, then we have 3. And then 2 mod 3, then we have 3. And if we also put these values into this formula, then we can see that this formula actually matches with our calculations. And for other cases, we can carry out the same program. We can count the 2-member subsets, or we can count the 4-member subsets, and then we have the same thing. Now here, we also have two important corollaries. The first thing is, suppose the value of c is 0, then this means that the sum of the elements in the subset is a multiple of n. Then the Mobius function mu vanishes, so that we have the formula of Jovovic. And in the second case, suppose the value of c is 1, then this means that the sum of the elements in the subset is 1 more than a multiple of n. And then in this case, the Euler's totient function vanishes. So here, we only have the Mobius function mu, and we have this formula. So this formula is quite similar to the formula of Jovovic. Now let me give a brief proof of this result. So here, my proof use the theory of partitions. So let's first take the first, so let's first write the elements in the subset in increasing order, so that we have 1 is smaller than or equal to x1, smaller than x2, etc. And then the tricky thing is we can subtract 1 from x1, we subtract 2 from x2, etc. Then we have the x primes. So we find that the x primes are in the weakly increasing order. So 0 is smaller than or equal to x1 prime, etc. And x vn prime is smaller than or equal to u minus v times n minus 1. And actually, these x primes form a partition with largest part smaller than or equal to u minus v times n minus 1. And also the number of parts is at most vn, because here we might have some parts of size 0, and then we just discard these parts. So here the number of parts is at most v times n. And we know that the number of partitions within a rectangle can be formulated by the Q binomial coefficient. So this means that we can find the generating function for the x primes, which is given by this capital R of Q, which is this Q binomial coefficient. And another thing is, if we sum up the 1 up to Vn, then this value is common to 0 for the first case and a half of n for the second case. So this is why we have two cases. And since we want the sum of the x is common to C mod n, then this means that we have the sum of the x primes is common to C mod n for the first case and a half of n plus C for the second case. Now, since the sum of the x primes is common to C mod n, then this means that we can apply the dissection formula to the generating function R of Q. So this means that if we apply the generating function, so here the counting function S is actually, we take out the coefficients of Q to the M, where M is congruent to C mod n, because here the exponent of Q is actually the sum of the x primes. So then we apply the dissection formula to the first thing, then we have this expression. And then for the second expression, we have the same thing. The only difference is here we have this -1 to the power L factor. And now we can see that the only thing we need to do is to give an expression of this capital R of this exponent of E. And how to find this, how to evaluate this capital R? Then we find that this capital R is can be actually given by this formula, that is U minus V over U times this binomial coefficient. And the computation is quite straightforward. So here, the product form of the Q binomial coefficient is this product. So here we just take the limit of Q to this exponent of E in each multiplicand, and the limit can be computed for each term. So when this power of K is not equal to 1, then the limit is 1, and when this power is 1, then we have U Bn plus K over K. And then after some simplification, then we actually arrive at this value. So the computation is just very straightforward. And if we substitute the value of R into the formula, then we have this one, and then we write the GCD as D, so that we can rewrite this summation in this way. And the inner summation is, so here D is GCD of L and N. Then this means that we can divide by D for L. Then this means that we can rewrite the inner summation in this way. And what's this inner summation? It is actually the Ramanujan sum defined in this way. And another important thing.
1 minute warning, by the way, just to let you know.
We have an expression of the Ramanujan sum. So here it is the product of the mobile function and then the totient function, honest totient function. So we plug all these things together, then we have the first formula for the first case, and then for the second case, we have almost the same thing, because the only difference is this factor -1 to the power L. So here, let me close my talk with some remarks. So here, the first thing is we can actually generalize the original set 1 up to U minus 1 to any consecutive to any UN minus 1 consecutive integers. Let's say this value, because here we can write each element in the subset xi as xi prime plus a plus 1. So the only difference is this a, but since we have Vn such subsets, then we have a times Vn, but it makes no sense when we mod n. And another thing is about the original EGZ theorem. So in the EGZ theorem, we have 2 and minus 1 integers in the subset. And if we use the idea of additive, then we can write it in this way, but we have no idea to simplify this expression for general S. So the question is, can we find other examples of capital S so that we have some nice forms for the number of desired n-member subsets? So this is the end of my talk. So any questions?
All right, great talk. Let's thank Shane first of all. Yeah, does anybody have any questions for Shane? So I think one thing that would be helpful for me is, do you mind going over again just what the main theorem is that you're proving in this? Because I understood the EGZ thing, but I got a little bit confused at exactly what your statement was.
Okay, so this is the main theorem. So it is just an extension of the formula of Jovic. So here we take U to be 2, and then V to be 1, and then C to be 0, then it reduces to Jovic's formula.
Oh, I see. That's cool. And do you use similar methods to what Jovic uses, or a little different?
So the method is quite different from them because they use the trigonometric functions, and then the computation is quite complicated. And then since I'm working on integer partitions, and then so I just borrow some ideas from integer partitions, and then I find that the computation is much reduced. Cool. And also we can make some extensions.
Yeah, so do you feel like these methods could be applicable to other types of problems?
Well, so it depends on the form of the original set. So when the original set is not nicely behaved, then the partition theory method might don't work.
Thanks. Any other questions? Now let's thank Shane again.
Thanks.